Chapter 11. Atmospheric composition. Air is a combination of gases such as nitrogen and oxygen, and particles such as dust, water droplets, and ice crystals. The Earth's atmosphere consists mainly of nitrogen 78% and oxygen 21%. The amounts of nitrogen and oxygen in the atmosphere are fairly constant over time. Earth's atmosphere contains variable amounts of solids in the forms of tiny particles such as dust, salt, and ice. The concentrations of some atmospheric gases are not as constant over time as the concentrations of nitrogen and oxygen. The concentration of water vapor in the atmosphere varies with the seasons, with the altitude of a particular mass of air, and with the properties of the surface beneath the air. During the past 150 years, the concentration of atmospheric carbon dioxide has increased due primarily to the burning of fossil fuels. Molecules of ozone are formed by the addition of an oxygen atom to an oxygen molecule. The ozone layer blocks harmful ultraviolet rays from reaching Earth's surface. As you see in the diagram to the left, ozone is 3 oxygen atoms, where an oxygen molecule is 2 and an oxygen atom is 1. Now, change in ozone with height. If you look at the blue line as you go from the base at 0, which is Earth's surface, up into the atmosphere, you can see that the amount of ozone increases up to about 20 kilometers. So it's at highest concentration at 20 kilometers, and it decreases as you go further out into outer space. The layers of the atmosphere, the lowest layer is called the troposphere, and it contains most of the mass of the atmosphere, and this is where weather occurs. In the troposphere, air temperature decreases as altitude increases. The tropopause is an altitude at which the temperature stops decreasing. Above the troposphere is the stratosphere, a layer in which the air temperature mainly increases with altitude and which contains the ozone layer. At the stratopause, air temperature stops increasing with altitude.
"15 to 35 kilometers above Earth's surface, a gas called ozone surrounds the planet. The ozone layer acts as a barrier between Earth and ultraviolet radiation from the sun. However, pollution has caused the ozone layer to thin, exposing life on Earth to dangerous radiation. Earth's atmosphere is made up of 6 layers. The second layer, called the stratosphere, contains the ozone layer. The ozone layer is made up of a highly reactive molecule called ozone, which contains 3 oxygen atoms. Ozone is a trace gas in the atmosphere. There are only about 3 molecules for every 10 million molecules of air. But it does a very important job. The ozone layer acts as Earth's sunscreen, absorbing about 98% of damaging ultraviolet or UV light. But the ozone layer has gotten thinner. Chemicals called chlorofluorocarbons, or CFCs, are the primary culprits in ozone layer breakdown. A CFC is a molecule that contains the elements carbon, chlorine, and fluorine. CFCs are mostly found in refrigerants, aerosols, and plastic products. When CFCs are exposed to ultraviolet rays in the atmosphere, they break down into substances that include chlorine. The chlorine reacts with the oxygen atoms in ozone and rips apart the ozone molecule. Areas of damage in the ozone layer are often called ozone holes, but that name is misleading. Ozone layer damage is more like a thin patch, with the thinnest areas near the poles. The ozone layer above the Antarctic, in particular, has been impacted by pollution since the mid-1980s. There, the region's low temperatures speed up the conversion of CFCs to ozone-damaging chlorine. About 90% of CFCs currently in the atmosphere were emitted by industrialized countries in the northern hemisphere. In 1989, the Montreal Protocol banned the production of ozone-depleting substances. Since then, the amount of chlorine and other ozone-depleting elements in the atmosphere have been falling. Scientists estimate that chlorine levels will return to their natural state in about 50 years. By then, the Antarctic ozone hole will shrink to smaller than 8 million square miles.
The mesosphere. Above the stratosphere is the mesosphere, in which air temperature decreases with altitude. Temperatures stop decreasing with altitude at the mesopause.
Just below the Arctic Circle, evening skies are filling with pale blue ripples. They appear just after sunset or just before sunrise and are called noctilucent clouds or NLCs. When viewed from space, the same atmospheric phenomenon is referred to as polar mesospheric clouds, or PMCs. Cora Randall, chair of the Department of Atmospheric and Oceanic Sciences at the University of Colorado, says, the 2016 season for noctilucent clouds began on May 24th, when NASA's Aeronomy of Ice and the Mesosphere Satellite, or AIM, spotted a puff of electric blue around the Arctic Circle. NLCs are Earth's highest clouds. Seeded by meteoroids, they float at the edge of space more than 50 miles above the planet's surface. The clouds are very cold and filled with tiny ice crystals. Those tiny crystals do a good job of scattering blue light from the rising or setting sun, hence their electric blue color. Noctilucent clouds appear during summer because, ironically, that is the only time the upper atmosphere at high latitudes is cold enough to crystallize molecules of water around specks of meteor dust. The role of meteor dust in forming NLCs is one of many discoveries made by AIM, which NASA launched in 2007 to study the mysterious clouds. James Russell, principal investigator for AIM at Hampton University, says, these clouds continue to reveal intimate details about how the atmosphere works. Each season yields new information. The first recorded observations of noctilucent clouds were made in the 19th century after the eruption of supervolcano Krakatoa. At the time, people thought the clouds were caused by the eruption, but long after Krakatoa's ash settled, the clouds remained. In those days, NLCs were a polar phenomenon confined mainly to the Arctic. In recent years, they have intensified and spread with sightings as far south as Colorado and Kansas. The reason may be climate change on the edge of space. A recent study by AIM science team member Mark Hervig and colleagues, published March 2016 in the Journal of Geophysical Research, confirms that the mesosphere, the atmospheric layer where NLCs form, has gotten colder and moister in recent decades. Both trends promote the formation of NLCs. Their results are consistent with a simple model linking the clouds to two greenhouse gases. First, carbon dioxide promotes NLCs by making the mesosphere colder. While increasing carbon dioxide warms the surface of the Earth, those same molecules cool the upper atmosphere, a yin-yang relationship long known to climate scientists. Second, methane promotes the clouds by adding moisture to the mesosphere because methane oxidizes into water as it rises in the atmosphere.
The thermosphere is the layer above the mesosphere and contains what we call the ionosphere. The exosphere is the outermost layer of the atmosphere, and it can be thought of as the transition region between the atmosphere and outer space. Energy transfer. Radiation. Incoming solar radiation is either reflected back into space or absorbed by the Earth's atmosphere or its surfaces. Energy transfer in the atmosphere. The total energy of the particles in an object due to their random motion is called thermal energy. There are three types. The first is radiation, which is the transfer of thermal energy by electromagnetic waves. Thermal energy is transferred from the sun to Earth by radiation. The second is conduction. That is the transfer of thermal energy between objects when their atoms or molecules collide. And last but not least is convection. Convection is the transfer of thermal energy by movement of heated materials from one place to another.
ways to transfer thermal energy. Let's look at conduction first. In conduction, energy is transferred by particles that are in direct contact with each other. The heat from the flame causes the tiny particles that make up the pan to vibrate faster. The pan particles bump against the butter particles, making them vibrate faster as well. As more and more of the vibrating particles come into contact with each other, the butter gains thermal energy and begins to melt. It has been heated by conduction. The second method of thermal transfer involves fluids, materials that flow, such as air and water. This method is called convection. Energy is transferred when matter flows from one place to another. Heating the air in the balloon creates warm air flows that are forced upward by cooler air flows that fall. The third method of thermal energy transfer is radiation. An example of radiation is the energy we receive from the sun. This energy is carried by electromagnetic waves that travel at the speed of light. When the sun's radiation reaches Earth, some is reflected back into space by the atmosphere, and some is reflected by Earth itself. The remaining radiation that reaches Earth is absorbed. It becomes thermal energy. You experience thermal energy when you touch a parked car that's been warmed by the sun.
Temperature. Particles have more kinetic energy when they're moving faster, so the higher the temperature of a material, the faster the particles are moving. To measure temperature, temperature can be measured in degrees Fahrenheit, degrees Celsius, or kelvins, which are shown on the right. Water freezes at 32 degrees Fahrenheit, which is equal to 0 degrees Celsius, which is equal to 273 Kelvin. Water boils at 212 degrees Fahrenheit, which is 100 degrees Celsius and 373 degrees Kelvin. The density and pressure of the layers of the atmosphere decreases, altitude increases. So as you go from the troposphere up to the thermosphere, you can see that the pressure is getting less and the density is getting much less. If you look at the picture on the right, normally the temperature at the ground level is usually warmer than up in the air. But a temperature inversion is when you have an increase in temperature with height in an atmospheric layer. It should decrease as it goes up, but as you see on the right side, we have the cold air on the bottom and the warm air on the top. If the land does not radiate thermal energy to the lower layers of the atmosphere, such as on a cold, clear winter night, when the air is calm, the lower layers of the atmosphere lose heat. The lower layers of the air become cooler than the air above them. Temperatures increase with altitude. That is what is a temperature inversion. In some cities, temperature inversion can worsen air pollution problems. The movement of air is commonly known as wind. In the lower atmosphere, air generally moves from regions of higher density and pressure to regions of lower density and lower pressure. Near Earth's surface, wind is constantly slowed by the friction that results from contact with surface, including trees, buildings, and hills. Higher up in the Earth's surface, air encounters less friction and the wind speeds increase. Cool air sinks. This creates an area of high pressure. Warm air rises. This creates an area of low pressure. Air masses move from high pressure to low pressure. This is what creates. Humidity is the amount of water vapor in the atmosphere at a given location on Earth's surface. Saturation occurs when the amount of water vapor in a volume of air has reached the maximum amount possible at that temperature. The amount of water vapor in a volume of air is relative to the amount of water vapor needed for that volume of air to reach saturation, and we call this relative humidity. The dew point is the temperature to which air must be cooled at constant pressure to reach saturation. The extra thermal energy contained in water vapor compared to liquid water is called latent heat. A process in which temperature changes without the addition or removal of thermal energy from a system is called an adiabatic process. Adiabatic heating occurs when the air is compressed, and an adiabatic cooling occurs when air expands.
We've all seen clouds build up on one side of the mountain, and then on the other side just dissipate into blue sky. Maybe you want to know why that happens. Like most natural events, this one has an impressive scientific term attached to it. It's called adiabatic cooling and heating, and occurs because of changes in air pressure. Here's some time-lapse video that shows what happens. Basically, as a particle of air encounters the mountain, it is forced upward. As air pressure decreases with altitude, the water vapor in the air condenses and becomes visible as a cloud. If there's enough moisture and the adiabatic cooling is strong enough, it rains or snows. Essentially, the opposite occurs on the other side of the mountain. The cool air sinks and compresses. Compression results in increased temperature. When temperature rises above the dew point, the cloud dissipates into invisible water vapor. In Wyoming, especially in winter, most of the moisture-laden air masses come from the Pacific, approaching our mountains from the west. So as adiabatic cooling occurs, more rain and snow is dumped on west-facing slopes. As warmer, drier air descends on the eastern slope, it accounts for another famous phenomenon of a plain, the so-called Chinook winds. So we've looked at clouds from both sides now. Knowing why they form and disappear does not diminish their beauty. If it weren't for our mountains and the dynamic processes that occur, Wyoming would be a much drier place and frankly, much less interesting.
Condensation level. Condensation occurs at the lifted condensation level, otherwise known as the LCL. Air above the LCL is saturated and thus cools more slowly than air below the ACL. Clouds. As warm air rises, it expands and cools adiabatically. The cooling of air mass as it rises can cause water vapor to condense. The condensation nucleus is a small particle in the atmosphere around which water droplets can form. When the number of these droplets is large enough, the cloud becomes visible.
Most of the time, if we pay attention to clouds at all, it's because of their effect on our local weather. Or maybe it's because they make a sunset prettier. But what you might not know is that clouds affect us every day, even if we're staring at a clear blue sky. The clouds we see when we look out the window are important components of a complex global weather system. They play a key role in Earth's water cycle, carrying huge amounts of fresh water and dropping it as precipitation. And depending on their properties and where and when they form, clouds can have dramatic effects on our climate, influencing the locations and severity of floods and droughts, and even the temperature of our planet as a whole. So by understanding clouds, we can better predict severe storms, the global distribution of fresh water, and the course of climate change. But what exactly are clouds, and how do they form? All clouds share the same basic ingredient, water. They're made up of water droplets or ice crystals that have formed from water vapor in the atmosphere. Although you can't see it or feel it, the air around us contains water even on the clearest summer day. The main sources of this vapor are evaporation, which is the escape of water molecules from the surface of oceans, lakes, and soil, and transpiration, the release of water by plants. As the sun warms Earth's surface, heat is transferred into the atmosphere along with water vapor. The warmer the air, the more moisture it can hold. But warm air doesn't usually stay near the surface for long. Like a hot air balloon, it rises. As it does, it cools. The colder the air becomes, the less water vapor it's able to hold. If the air becomes cold enough, it reaches a state called supersaturation, which causes some of the water vapor to transition back to a liquid or solid state. Water molecules in the vapor form around tiny particles of dust, ice, sea salts, and pollution suspended in the atmosphere. These particles, called condensation nuclei, serve as the starting point for the formation of water droplets and ice crystals. With this final step repeated billions and billions of times, the water that's been in the atmosphere all along is suddenly visible. And a cloud is born. While we can now see the cloud, the individual droplets or ice crystals are tiny, which is why they remain airborne. But they can combine to form larger drops or crystals. And if they become large enough and too heavy to stay aloft, they'll fall as rain, snow, sleet, or hail back to Earth's surface, where the water in them came from originally.
As air masses rise, it cools. However, the air mass will continue to rise as long as it's warmer than its surrounding air. When an air mass sinks back to its original position and resists rising, it's considered stable. The stability of air masses determines the type of clouds that form and the associated weather pattern. Stable air has a tendency to resist movement. Unstable air does not resist vertical displacement or upward rising. Clouds can form when moist air rises, expanding and cooling enough for water vapor to condense. Clouds can also form when air is forced upward or lifted by mechanical processes. What you're seeing here is called orographic lifting. It occurs when an air mass is forced to rise over a topographical barrier. Atmospheric lifting. Air could be lifted by convergence, which occurs when air moves into the same area from different directions and some of the air is forced upward. This process is even more pronounced when air masses are at different temperatures and they collide. A is called a convective. That is the convection of air moving together, coming together over cold air over warm air, which causes the cloud formation. Then the second one is a frontal. On the upper right is a frontal when we have warm air hitting a cold air front, and that causes precipitation. Bottom left is the orographic, which we just talked about, and the bottom right is a convergence. That's when you get two warm air masses.
Being able to predict the weather by observing cloud formations is a skill that is somewhat lost on us modern humans. Most of us can easily look at a cloud and see the unicorn or ice cream cones, but very few of us can look at clouds and see the approaching cold front. Fortunately, being able to predict the weather is easier than one may think. Clouds can easily be broken into four categories. These categories are high clouds, middle clouds, low clouds, and clouds with vertical growth. Clouds are also identified by shape. Cumulus refers to a heap of clouds. Stratus refers to clouds that are long and streaky. And nimbus refers to the shape of rain, because we all know what rain looks like. High clouds form at 16,000 to 43,000 feet. Basically, these are the clouds that you only encounter on the top of really high mountains or at the cruising altitude of a jet airplane. Due to the extreme conditions at which they form, they tend to be comprised primarily of ice crystals, and they do not block sunlight. High clouds include cirrus, cirrostratus, and cirrocumulus. Cirrus clouds are white, wispy clouds that stretch across the sky. By all accounts, cirrus clouds indicate fair weather in the immediate future. However, they can also be an indication of a change in weather patterns within the next 24 hours, most likely a change of pressure fronts. By watching their movement and the direction in which the streaks are pointed, you can get a sense of which direction the weather front is moving. Cirrostratus tend to be sheet-like and cover the whole sky. You can usually tend to see the sun or moon through them. Their presence usually indicates moist weather within the next 12 to 24 hours. Cirrocumulus clouds tend to be large groupings of white streaks that are sometimes seemingly neatly aligned. In most climates, these mean fair weather for the near future. However, in the tropics, these clouds may indicate an approaching tropical storm or hurricane, depending on the season. Middle clouds form at 6,500 to 16,000 feet. They are comprised of water and, if cold enough, ice, and they often block sunlight, but not always. Middle clouds consist of altostratus and altocumulus. Altostratus are gray and or blue clouds that cover the whole sky. They tend to indicate a storm sometime in the very near future, since they usually precede inclement weather. Altocumulus are grayish-white clouds blanketing the entire sky. They tend to look like large, fluffy sheets, in which there is a lot of contrast between light and dark. Sun does not pass through them. If you see them in the morning, prepare for a thunderstorm in the afternoon. Low clouds form below 6,500 feet. These clouds are the ones that like to hang around, just above tall buildings. These clouds tend to contain water, but can also be comprised of snow if the weather gets cold enough. These clouds block sunlight and can bring precipitation and wind. Low clouds include stratus, stratocumulus, and nimbostratus. Stratus are low-lying solid clouds. that are often formed when fog lifts off the ground. They obviously look like an elevated fog. Often they bring drizzle or light snow. Stratocumulus are low-lying, bumpy and gray clouds. They do not bring precipitation. They also do not cover the entire sky and tend to come in rows and patches. Nimbostratus is your standard rain cloud. It is a large flat sheet of gray cloud with a little bit of differentiation. If you see these, chances are it's raining outside. And last but not least are clouds with vertical growth, which tend to have a base that hangs really low, around 5,000 feet, and a top that climbs really high, over 50,000 feet. Clouds in this category include cumulus and cumulonimbus. Cumulus clouds are your stereotypical white cotton ball clouds. So long as the clouds remain low clumps floating across the sky, there will be fair weather. However, you need to keep an eye on these clouds, because any vertical growth can indicate the start of a large storm. Cumulonimbus are cumulus clouds that have grown vertically into an anvil-like shape. The anvil tends to point in the direction the storm is moving. These clouds bring most dangerous weather, such as rain, lightning, hail, and tornadoes. All right, now that we know what the basic types of clouds are, we need to look up at the sky. Go outside and look at the sky. If there are no clouds in the sky, then the weather is fine. Assuming there are clouds in the sky, we now need to identify them. First, determine if you can see the sun or moon through them. If you can, then you are looking at high-altitude clouds. If the clouds are thick, then there's a chance of poor weather a day or two in the future. To determine when the storm will arrive, observe whether or not the clouds appear to be moving. If they appear stationary, it is a slow-moving front and probably won't arrive for over a day. If they appear to be moving, then the change in weather will be there faster. You can tell which way the storm is traveling by the direction the clouds are pointing. If you cannot see through the clouds, chances are that you are looking at middle or low altitude clouds. First, determine which of the two you are dealing with by observing shape, color, and other more obvious giveaways. Are they covering the entire sky? Then they may be middle-altitude clouds. Do they appear to be gray with a blue tint, or fluffy white gray clouds with a lot of contrast between light and dark? If yes, then these are middle-altitude clouds, and you should prepare for rain within half a day. If you answered no to any of those questions, then check for low-altitude clouds. These tend to appear low and often engulf mountains and buildings. If it looks like an elevated fog, expect drizzle, if it isn't already. If it is rows of low, dark, lumpy clouds, then the weather is otherwise okay, but watch for further developments. If there is a low, dark, gray sheet, then it's probably raining. If it's not, quickly go get your umbrella. If your clouds are low, fluffy, and white like cotton balls in the sky, then the weather is okay. However, keep an eye on these for any vertical growth of the cloud upwards into the sky, like turning into anvil shapes. These clouds can unexpectedly change from fair weather indicators into violent thunderstorms.
Now, clouds are classified by their altitudes at which they form and by their shapes. Cirrus means wisp-like. Stratus is layered. Cumulo means heap or pile. Alto means high, and nimbus means cloud. So you see all the different examples that are over here on the right-hand side. We're going to go through them one at a time. Cumulus clouds are the puffy, lumpy-looking clouds that occur usually below 2,000 meters. If you look at the right, those are the ones that most people draw. They're the ones that look like cotton balls. Another type of cloud that forms at heights below 2,000 meters is a stratus. It's a layered sheet-like cloud that covers much or all of the sky. So the difference is the cumulus will be high and large, where the stratus are usually low and long. The middle clouds, the altocumulus, which means high heaps, form between 2,000 and 6,000 meters, and they're made up of ice crystals and water droplets. On the right of that, different from the altocumulus, is the altostratus, which is more like a sheet. So it's a sheeted. High clouds made up of ice crystals form at around 6,000 meters where temperatures are below freezing. Some are like the cirrus clouds on the left, which are wispy and they have an indistinct appearance. And on the right, you see the cirrostratus, which are high clouds, but they're very thin and they're almost like a layer. Vertical development clouds. If the air that makes up a cumulus cloud is unstable, the cloud will continue to grow upward through the middle altitudes as a towering cumulonimbus. If the conditions are right, it can reach the troposphere. A cumulonimbus cloud forming a towering mass with a flat base at fairly low altitude and often a flat top, as in thunderstorm.
Soar over an increasingly unstable atmosphere. A tornado watch is issued. An isolated thunderstorm rises high into the atmosphere. Precipitation begins to fall. Sheets of rain reflect, refract, and disperse sunlight into the visible color spectrum. Cloud-to-ground lightning activity increases as the storm begins to rotate. A tornado warning is issued. Source: radar-indicated rotation. A confirmed tornado has been reported. The explosive updrafts flatten into the ceiling of the troposphere. At sunset, the isolated thunderstorm creates a dance of light and color. Decreasing sunlight reveals more and more lightning activity. Bursts of cloud-to-air lightning reach out into the naked sky. Downstream, mammotus clouds sail underneath the storm's anvil. A full moon emerges from behind the storm clouds. Icy cirrus cloud crystals refract moonlight into a lunar halo.
Now, precipitation. In essence, when droplets become too heavy to remain suspended in the cloud, they fall to Earth as precipitation. Snow, sleet, and hail. The type of precipitation that reaches Earth depends on the vertical variation of the temperature in the atmosphere. forms of water that fall from clouds to the ground are precipitation. As you just saw, rain, snow, sleet, and hail are the four main types of precipitation. Now let's watch Jim.
Oh yes! Oh yes! Yes! We got it, baby! We got it! We got it! We got it! Woo! We got it! We got it! Yes! Yes! Listen to that! Listen to that! Listen to that! Listen to that! Oh baby! Oh baby! Just got it! Just got it! Oh! Again! Again! That's a twofer! That's a twofer, baby! Yes! Yes! That's a twofer! That's a twofer! Twofer, baby! Twofer, oh baby! My goodness! Oh my goodness! Yes! 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 Again! Yes! That's a three! You gotta be kidding me! 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 Pirac! Pirac! 3, baby, in 10 minutes. Oh my god! Oh my god! The winds have really picked up in here. And there's another one! And there's that's another number! One. You gotta be kidding me! You gotta be kidding me! Wow! Wow! You can have your $500 million jackpot in Powerball or whatever the heck it was, but I'll take this, baby. Four lightning strikes, four episodes of thunder snow. I can hear thunder. So we had another one. So we actually had five strikes, five thunder. This is just a total change. Literally within an hour. Was that another one? Was that another one? Was that? Oh my good, dude, that's number 6. Dude, that's number 6. You gotta be kidding me. You gotta be kidding me. Dude, I'm telling you, this is Chicago. This is Chicago all over again. We're just sitting in the middle of it.
The water cycle. Water moves from Earth to the atmosphere and back to Earth in the water cycle. And we talked about this in earlier chapters when we were talking about runoff and groundwater. And now, since we're talking about condensation and precipitation, we've finally gotten through the entire water cycle.